Hey, I'm JP from Sourdough. If you've seen my recent talk on procedural generation, this video is a companion walkthrough of the procedural generation visualizer I built to make those ideas a little bit more concrete. The tool here, the procedural generator, is live on itch.io and fully open source on GitHub. Both links are in the description. I'd recommend pulling it up alongside this video so you can experiment in real time as we go. I've added chapters so you can pause, jump around, or come back to specific sections later. Without further ado, let's get into it. To get started, click the Get Started button on the splash screen of the tool. This brings you into the main generation UI, which lives at the top right-hand corner of the screen. The first thing we control is map size, with width and height. The visualization tool uses Godot's TileMap layer system, but the actual generation logic is written in a clean, object-oriented way, so the algorithms themselves are portable and reusable. We'll touch on that more when we look at the code later. Below that is a drop-down where you can choose which generation algorithm you want to experiment with. When you select one, the UI dynamically populates with the parameters specific to that algorithm. Let's start with the simplest example, rooms and corridors. I'm going to set the map size to 40 by 40 for this demo. Each input field shows the expected data type. You can see it here in the placeholder text. These will either be integers or floating point values. For this run, I'm going to use the following parameters. Our max rooms of 8, our minimum rooms of 4, max room height of 15, as well as our max room width of 15. With that, we can click go and see our map get generated. You can move around the generated space using WASD and zoom with Q&E or the mouse wheel. For large-scale experiments, this navigation becomes essential since the tool can generate very large maps. If you want to hide the UI entirely, press X. Press it again to bring it back. As you can see, we can run this a few times and generate a few different options. Moving on to the more complex algos, I want to spend a moment on the noise generator. The same ideas apply to several other systems here, especially anything that uses floating point parameters. For Perlin noise in particular, it's best to work at larger map scales, usually 100 by 100 or bigger, so you can clearly see how each parameter affects the output. The first parameter to understand is frequency. You can think of frequency as scale. It controls how large or small the features on the noise map are. Lower frequency values produce larger, smoother features, while higher frequency values produce smaller, more chaotic detail. If the frequency gets too high, the map can start to look a little bit like random static. For a 100 by 100 map, a good starting range is usually around 0.002 to 0.004. For the purposes of the video, I'm going to put in 0.003. Next up are octaves. Octaves control how many layers of noise are combined together. Each additional octave adds another layer of detail on top of the previous one. With fewer octaves, say 3, the map tends to have broader, simpler shapes. As you increase the number of octaves, 4, 6, or more, the result becomes increasingly complex, with softer edges or more variations across the map. For the purposes of the video, let's use a nice even value of 4. Next, I want to talk about one of the more difficult to understand parameters of a Perlin noise generator, and that's lacunarity. Lacunarity controls how much finer the detail becomes with each added octave. Well, so remember our octaves are each additional layer. So technically what lacunarity does is for each successive layer of noise, it multiplies the base frequency for each successive layer. So whatever our base frequency is, in this example we see it's 0.003, what lacunarity does is for every additional layer, it multiplies this original frequency. So we end up getting finer and finer detail with higher multiplicatives, versus we can have blunter and blunter detail if we use a number between 0 and 1. For the purposes of this example here, we're going to use 4.5. Higher lacunarity values introduce sharper, more intricate detail at smaller scales, especially around edges and transition regions. It's a very useful tool to create kind of uneven edging across your noise map. You'll see that when we run the example in a moment. And then finally we have gain. Gain controls how much influence each new octave layer has compared to the previous one. A higher gain means later layers of noise have more weight, which can significantly reshape the map as octaves are added. A lower gain keeps the base shape more dominant. A good default value to start with is around 0.5. You can adjust from there depending on how aggressive you want the layering to be. With all of our parameters in place, let's run a few generation cycles. Here we go. This is a good one for me to talk about. Looking at this, while we have kind of a blob up here, down here is really more of the granular detail that I was talking about. Noise maps can be excellent for generating things like continental silhouettes. In a video game, you might consider this a world map. We can run a few more where we almost imagine that this black is ocean, the gray being landmass. Kind of generates a continental-like appearance. I'd strongly encourage you to experiment with the values in your own study of procedural generation, especially in combination with larger map sizes. This setup is particularly effective, as I said earlier, for generating continental silhouettes or large-scale terrain shapes, places where you want structure first and then detail second. Another classical use case of noise maps is for elevation. My procedural generation tool does not show or does not have the capability currently to show this elevation feature. However, there are plenty of examples out there on the internet. Next up is the most mathematically structured algorithm in the tool. This being cellular automata, often referred to or in conjunction with the game of life. This is what I like to think of as the most organic generator in the set. Instead of placing structures directly, we simulate simple rules about life and death and let patterns emerge over time. In this implementation, floor tiles are considered alive, and wall tiles are considered dead. In the visualizer, floor tiles are gray, wall tiles being black. That framing will make more sense once we step through the rules. Starting in CA, I want to talk about placement or the seed framing. Everything starts with an initial seed value, defined as a floating point value between 0 and 1. This represents the probability that a cell starts out alive. Internally, each tile rolls a random value between 0 and 1. If that value is greater than the placement threshold, the tile becomes a living cell. For this example, I'll start with a value of 0.4. This usually gives us a fairly sparse initial distribution. In order to move on, we need to talk about the neighborhood definition. Each cell evaluates the number of neighboring cells around it. In a 2D grid, I'm using the 8 neighbor system, which makes sure to include diagonals. This tends to produce smoother and more readable results for terrain and cave-like structures. Keeping in mind our neighborhood definition, the survival threshold determines how many neighboring living cells a tile needs in order to stay alive. If a living cell has fewer neighbors than this threshold, it dies and becomes a wall tile. For a more dramatic consolidation effect, I'll use a value of 7, which strongly favors dense clusters and aggressively removes isolated cells. The birth threshold works in the opposite direction. If a dead cell, a wall tile, has more living neighbors than this threshold, it becomes alive in the next iteration. I found a value of 3, produces a nice balance between growth and restraint, leading to maps that feel organic without completely filling in. Finally, we have an iteration count. This controls how many times the simulation runs. Each iteration applies the same survival and birth rules to the entire grid, allowing patterns to reinforce and smooth out over time. For this demo, I'll run 4 iterations, which is enough to clearly show how the system evolves without over-homogenizing the result. Now that our parameters are in place, let's run a few generation cycles. As you can see, CA, or cellular automata, produce very natural looking structures, smooth caves, clustered regions, and flowing boundaries. This approach works especially well for things like cave systems, forests, bacterial growth, city sprawl, or any system where you want emergent structure rather than rigid geometry. It pairs particularly well with the noise-based methods, where noise defines large-scale structure and CA refines it into something that feels alive. Just for a quick mention, I'm going to bring the map size back down to something like 30 by 30. And I want to showcase the Drunken walk real quick. This is a classic random walk algorithm, where one or more agents move step by step in random cardinal directions, carving paths as they go. You can control both the number of steps and the number of walkers, which lets you create anything from thin tunnels to broader interconnected structures. For this, on our 30 by 30 map size, let's start with 3 walkers and give them 80 steps apiece, and we can adjust on the fly. So I'm going to zoom back in so we can kind of see our example a little bit better. I'm going to give them a little bit more. Let's go with 200. That might be a bit much, but let's see. No, that's perfect. You can see the Drunken walk kind of, while it is a little bit too random, it does create a nice, non-homogeneous looking structure. Creating biases into this algorithm can do great for things like river flows. I'm a big fan of the Drunk walk algorithm just for some of the more unique structures that it can create. I'm not going to do a full line-by-line code walkthrough here. Instead, I want to explain how the system is structured so you can reuse or extend these generators in your own projects. I'd encourage you to explore the repository directly if you want to dig into implementation details. So, to get into the code here, at the core of everything is the GameMap class. This is the class that we have open here. It's a lightweight, ref-counted GD script object that holds a 2D array of map cells. When it's constructed, it initializes the grid with wall tiles by default. You can look here at the constructor, which defines the map height, the map width, creates a rect of those, and then fills the map. And the fill map function you can see here with making wall cells throughout. We'll get into what a wall cell is in a minute. There's also this simple debug render function here, which prints the map to the GD console. It's useful when you want to test generation logic without rendering a full tile map. This is what our game map gets filled with. This is the abstract class called mapCell, which holds values for our debug. The position, the glyph for our debug, so we show when we print to console, and whether it's walkable or not. This is just an abstract class to inform our floor cell, which when constructed sets our position, sets the glyph, and floor is obviously walkable. And then our wall cell as well, which does the same thing, but has a different glyph for the debug renderer and a different walkability. We also have an abstract class to define our dungeon generators, which I'll get into in a moment. This just makes sure that all dungeon generators have a game map class and it's universal across all, and that they all have a GenDungeon class, which you'll find is the money-making method when it comes to editing our game map. Let's get into the generators themselves. Each generator is implemented as a separate ref-counted class. They're fully modular, lightweight, and object-oriented. They all extend the dungeon generator class. To keep things concrete, I'll use the Drunk walk generator as an example. We see our fields here at the top. Our constructor, which is universal to all generators, our GenDungeon function, and then our heavy lifting function, which for this particular algo is the takeWalk function. Just for a brief deep dive, all it does is create walkers at random start points, then iterate over the number of steps in 1 or 4 random cardinal directions. This bound step helper function ensures we don't walk outside of the bounds of our game map. So from the top, we see our fields, where we see how many walkers we want, how many steps, which tiles have been walked upon in an array, and then a step counter. Start point as well. Our constructor, right here, takes the UI values that we saw previously in the actual tool. When we want to generate a dungeon, for each walker that we have, we set a random start point and then send them on a walk. All of the dungeon generators don't return anything, they directly manipulate the game map. So when you want to mess with your end product, all you need to do is pass the universal game map object around. In the tool, generators are run intentionally, one at a time. The goal here isn't to stack techniques, but to understand how each algorithm behaves in isolation. This makes it a little bit easier to build intuition before combining approaches in a real game. Once a map is generated, you're free to use it however you want. Bake it into a TileMap, export it, or keep it purely data-driven. If you're curious about how I convert the generated map into a rendered tile map, you can take a look at the bake map function in the generation handler class. This generation handler class ties in all of the tools, all of the subtools within the tool. It populates the UI, gets user input, and makes everything work correctly. The function in question is all the way down here at the bottom. This bake map function, which writes our data into the TileMap layer. I hope this walkthrough helped build intuition around procedural generation and map building systems. The project is fully open source, so feel free to explore, modify, or reuse the code in your own work. You can find a link to the tool in the description below, as well as the link to the GitHub repo. Here on my itch page is where you can play the procedural generator tool. There's also a link in the description here to the source. Thanks for watching. I'll see you in the next one.